agenda for this session. Talk a little bit about the introduction, about things that you already know, most likely. Talk about a little bit about the use cases that we try to address with MySQL Replication and things that we try to enhance to enable further use cases down the line in the future. Talk about things that we've done in MySQL 8, and some of these things we actually backported into 5.7. Some of our users actually requested a few things to be backported, and those that made sense to backport, we actually did it. Try to finalize this with an overview of the roadmap, and then conclude the session. So nothing very fancy, but I'll try to go a little bit fast because there's a lot of things to show, new things to show that are in MySQL 8 with respect to replication and specifically about group replication. So a little bit of context. Everybody in this room knows this, you know, today everything is distributed, everything everything is distributed. There's a lot of data running through our systems. There's a lot of different systems to manage and operate, and there's a lot of concerns with respect to efficiency, performance, and so on and so forth, right? So this is the context that we have in today's IT universe, if you will. And of course, in this area, MySQL, or replication in particular, plays a big role. Not just in MySQL, but replication overall in any system that we have today. Whether it's to build HA, whether it's to build scale-out systems, whether it's to build kind of live backup systems, and so on and so forth. Replication and redundancy in particular is a big property of today's systems. And it's quite simple, or at least it looks quite simple, right? Usually replication builds on top of an architecture like this. There's some change that is performed in some server, and then it's replicated across to some other server, and then both servers are brought up to date. The problem is in the details, and there's a bunch of details when we talk about distributed systems that we have to cater for. And we try to hide those details and caveats from the user and handle them ourselves. MySQL replication is not really much different from the other general architecture picture that was in the previous slide. It's very simple from the high-level overview. There's a master or a primary. There's a log, the bin log that is shipped around. And then there's a slave or a secondary that ingests this log, and it's brought up to date with the primary. MySQL replication is almost 20 years now, if not 20 years already, and it started by building on this master-slave replication architecture, where you have the bin log, and then you have the MySQL protocol connecting the slaves and the master, and then you have the bin log being moved around between these two, let's say, concepts. With the introduction of group replication, we kind of pumped up that communication framework pipe there, and we added more functionality or more features into this relationship or intercommunication between the two servers, like the master and the slave. And we added things like total order delivery, atomicity in message delivery, group membership management, automatic group membership management, and so on and so forth, so that we are able to build more advanced replication features on top of this. And as I mentioned earlier, to take away from the user responsibility the need to do a lot of the operations manually or build tooling on top of it to do it manually. So when we get to the point that we have things like total order delivery and group membership and so on and so forth, we have a very nice framework to be able to build on because things like failures and message delivery become total ordered in the flow of the replication stream. So it's easy to reason about how the system looks like after a failure, what should be done, and so on and so forth. So it becomes a lot easier to automate this. But I'm going already a lot into the details. Let me just carry on with this. And this is just a description of the bin log. The bin log is a logical log. I'm sure that pretty much everyone in this room knows about the bin log if you're operating or deploying and using MySQL. Who here actually uses MySQL Replication? So that's it. I don't have to talk more about it. Just a quick recap. As I mentioned earlier, MySQL Replication has been in MySQL since 3.23. It is, since back then it was a synchronous replication between a master and slave, meaning that I execute a transaction on my master, it gets written to the log, and eventually this log is copied to the slave. Since 5.5, we introduced this semi-synchronous replication where it adds a little bit of guarantees to this interaction between the master and the slave, whereas if the master tries to commit something, it will wait for the slave to acknowledge that it has received it, and only then finalizes the commit and externalizes the changes to the application. And since 5.17, we introduced this group replication plugin to introduce these features that I mentioned earlier, like automatic group membership, the failure detection, and so on and so forth. So to make it, a built-in clustering solution into MySQL. The interesting point is that a lot of the framework and technology used to build this was already existing, or already existed at the time, right? So it's the same bin log, it's the same monitoring infrastructure with performance schema, it's the same applier of the bin log, it's the same everything. But as I mentioned, the really hard work was done at the communication level between masters and slaves. So we want to replicate, automate, integrate, scale, and enhance the overall user experience with MySQL and MySQL Replication. As systems become distributed, as systems become larger and bigger, it becomes a lot harder to manage those, right? It becomes really hard to understand, this thing happened here, why did it trigger some weird thing there? It becomes harder to monitor, observe, right? So we need to build automation in all of these things. And as soon as you build automation into these things, it becomes a living and breathing entity on its own. So we need all of this to be easy to manage and interact with. So these are the kind of things that we're trying to addressing as we move forward. So we want to replicate, and for highly available infrastructures, we're trying to push group replication forward to cater for all the use cases that people are hitting with traditional asynchronous replication. It's not that one is going how should I say it? It's not that one is going to replace the other altogether, because there's no silver bullet for each and every use case that you may be running into. But for the average use case where you want to build things with HA, we believe that group replication is a good path forward. Automation, a lot of the things related, for instance, related to failovers and failure detection and all of these things, automatic recovery and so on, are built and automated through group replication as well. We want to continue to extend the bin log, to be able to, the bin log is a very interesting component of this story, because its primary usage was actually just, for replication, right? But as soon role-based replication was introduced in 5.1, it enabled more use cases like, okay, maybe I can use the bin log as a change stream, so I can build ETL on top of it, or CDC on top of it. And as people started to rely more and more on the bin log to do things like moving data from MySQL into some other systems and so on and so forth, we've got some requests, even from our users, can you please extend the format to include this and that information, because I'm doing this with the bin log and with the MySQL server in that loop, so I need to have more information in the bin log to be able to, glue these two systems together. So we've also been enhancing the bin log format to cater for this as well, for these use cases as well. And of course, I mentioned, we introduced group replication and the asynchronous replication, they don't necessarily, one doesn't necessarily replace the other. In fact, they actually complement each other. For things like DR, implementing DR with group replication or geographical replication between clusters and so on, we can use asynchronous replication between the two. And the fact that the same technology was used to implement one, right? It makes things so much more easy to relate to and easy to interact with, because it doesn't feel an alien thing at the end of the day. It's still the same performance schema tables for monitoring, still the same bin log, it's still the same everything, right? Maybe you have two new performance schema tables to look into, but that's about it. And furthermore, all this complexity was later simplified with things like the MySQL shell that provide you a one-stop tool to interact with these systems. Even if the group replication part doesn't automate everything, the shell itself can already help you to operate the system with much easier or simpler interfaces. So we also want to continue to enhance the overall user experience with the InnoDB cluster and group replication and so on and so forth. And as I said, as you keep building automation into these systems, it becomes a living, breathing entity on its own. So it's really hard, when things go south, to diagnose and so on and so forth if you don't have any help from tools like the MySQL shell or even MEM and so on and so forth. All right, so let's talk a little bit about things that we have enhanced in MySQL 8 that allows us to continue to cover all these different axes of things that we want to improve. So one thing that we introduced very recently in group replication is the ability to specify a different consistency criteria for queries or statements or transactions that you run through a group, right? You can, in group replication, or let's say in InnoDB cluster, if you're going to update some table, you go through the primary, you update the table, and so on and so forth. And then maybe if you're reading, you connect to the read-only port of the MySQL router, and then it routes you to one of the slaves, right? But the fact that replication is still asynchronous, right? You updated the primary, eventually it's propagated to the slave and applied on the slave or the secondary. It means that if you go to the secondary immediately, you might not read the update that you did on the primary. It's still in transit, right? So some people actually have stronger requirements in terms of guarantees, consistency guarantees, or no lag kind of guarantees when they are engaging and reading from the cluster. So we introduced these options to be able to do things like, if I'm reading from the cluster, I want to read from the most up-to-date snapshot of the data, regardless of which server I engage. If I updated some table on the master, I want to wait for this update to propagate to the server that I'm reading from before I actually run my queries. So in this case, the application updated, it set x equals 5, where it was 1 previously. And then the application tries to read the same x from a different server, and it says, okay, I want to synchronize my read operation before the read operation execution actually takes place. So this means that, okay, I'm going to see if there's any in-transit or missing transaction to be applied before I actually do the read. So in this case, the application will read x equals 5, even though it read immediately after the update from a secondary. So this gives you the guarantee that, okay, I will synchronize with the rest of the group before I actually do my read operation. You can also synchronize after and say, I want to pay the synchronization penalty on updates instead of my reads, right? So what this basically means is that the same case here, you write to the primary, it replicates to all the secondaries, it is applied on all secondaries, and only then the application gets the commit acknowledgement. So it's almost like synchronous replication if you think of it, because once the commit operation is returned to the application, every other server in the cluster will have this change applied. So if you go to the secondary, you read your change that you've done on the primary immediately. And this is a weaker guarantee in the sense that some people say, okay, I want everything to be eventual. I don't care, right? But if a failover happens, what I cannot have is if I go to the primary, I see old data, right? So let's take the case that, in this case, we updated B, we set X equals 5 in B, and B failed. So the system will bring in A to be the new primary, but the new primary could have this operation, its backlog still. It was not applied because it was operating under eventual consistency. So if I try to read from my primary, because the application doesn't even know because it's going through the MySQL router, so the router has hidden this failover from the application, it might just be weird that I read from the primary again and I see old values. It's just weird. So this consistency criteria basically says if you fail over, you do not allow the application to read unless the backlog is fully applied. The replication backlog is fully applied on the new primary. So this was all introduced in 8.0.14. And this is basically what I said, this slide here. And you can combine both. You can say you can combine both before and after, so that you say my application has a very strict consistency requirement. It needs to start the transaction on the most recent snapshot of the data, and by the time it finishes, I want every other server in the group to already have this transaction applied. So this is the strongest consistency guarantee. If you only set it to after, for instance, you start executing on the current snapshot of the data on the server that you're executing your change, your transaction, right? But in this case, with before and after, you wait for the most recent snapshot, you start executing, and then you synchronize at the end as well. Yep, and you can change this consistency, the different consistency options using this group replication consistency variable. So operations, we added this in MySQL 8 and then backported it into 5.7. We added this option to fence servers if they are evicted from the group. So service operating, some network partitioning happens, and the group decides to, I suspect that you're dead, or you're really dead. To me, you're really dead, so I'm just going to kick you out and remove you from the membership. If this guy is evicted from the group, it will set itself to read only. This prevents things like, maybe some application is connected to this guy that was evicted, and I don't want it to, and it was the primary, so it was evicted. I don't want it to drop out of the group and remain read-write, because then I will create kind of an artificial split brain in this case, because the world may have partitioned in such a way that the application runs off with A in this case, and the rest of the system remains with B and C, and then you have part of your application writing to A and part of your application writing to B. So in this case, what happens here is that A sets itself to super read-only and isolates itself from the rest of the application in terms of updates. Okay, but some people said, well, that's good, but not enough, because what I would really like to is for A to get out of the picture altogether. You know, I don't even want to allow stale reads if if A gets dropped out of the group. So we took this one step further, and if A drops out of the group, it basically shoots itself in the head and disappears from the system, basically. So the application will, there is the hypothetical application that may have partitioned together with the server will just not have a server anymore to connect to. And this was also backported into 5.7. Another thing that was backported into 5.7 was the ability to control which server would be selected as a new primary next. So you can assign different weights for the election, and then depending on the weight setup, a new primary will be selected. The new primary will be selected according to this setup. So you can basically influence the election mechanism of the new primary. And we've also introduced in 8.0.13 a way to say, okay, I want to switch primary. I want to switch my primary on demand. I want to trigger an election, and I want to actually say this will be the new primary, not some randomly chosen primary or some primary chosen according to the member weights. I want this server to be the next primary. Maybe you're doing, I'm taking the existing primary to do some maintenance, so I just want to trigger everything, the failover right away, the switchover right away, before I take it down and so on. So this is what was introduced in 8.0.13. So this all happens online. You don't have to stop your workload. You don't have to do anything. The system will reorganize itself with no downtime. Yeah. And the same mechanism is actually used to switch between single primary mode to multi-primary mode. Before this was introduced, you would have to stop the cluster, switch the mode, and then restart the cluster altogether. Right now, you can just go back and forth between the two modes online without having to stop anything at all. And this is an interesting thing. Of course, you want to detect failures as soon as possible, and you want the membership to rearrange itself as soon as possible, and so on and so forth. But some users said, okay, but I'm running group replication or InnoDB cluster in a set of VMs. I'm backing up the VM or doing some maintenance on the VM every week on Saturdays at night. But this maintenance thing requires that I freeze the I/O on the VM. So what this means is that, if the I/O is frozen, you cannot send messages across to other guys in the cluster. You cannot say, I'm here, so you don't have to evict me if you're going to. So what people asked for was a mechanism to make the failure detector less nervous. In the sense that, okay, you may suspect, but you don't have to kill me right away. You don't have to evict me right away, right? So in this case, C is saying, well, I think that A is gone, right? And B says, okay, let's hold your horses. Let's give it some time. Maybe it's in this maintenance thing that our operators are doing. So let's see if it comes back within a certain number of minutes. And eventually A comes back. That's a good thing that they waited, because you don't have to rearrange the membership, you don't have to do this and that. But there's always a trade-off, right? Because in between the time that A was down or unreachable, B and C had to keep a log, keep track of the messages that A could have lost or has not received yet, right? So that when A comes back, A will say, okay, I was away for a few minutes. Please send me the rest of the messages that I missed. and B and C will send A the missing messages. This all happens without you ever, or the user ever, noticing anything at all. But it's what happens under the hood. It's a minor detail. And one thing we also did in 8.0.16 is, okay, A never really got back in time, right? It was, these other two guys said, okay, hey, he's really gone, he's not responding, so it's really unreachable. Let's just remove it from the group immediately. And A eventually learns about the fact that, wait a minute, I was in this group, but now I'm not anymore. So can I join again? Can I rejoin? And A will do exactly that. It will say, okay, I was evicted. I realized that I was in the group, but I'm not anymore. And I will automatically, proactively rejoin the cluster so that I don't, so that I don't stay here and the DBA or the operator has to come in and add me back to the group. So this thing, it's more or less like between a master and the slave. If the connection goes down, the slave tries to reconnect for a number of times, and there's some interval between the times that it tries to reconnect. It's the same kind of mechanism here, right? So A will try to rejoin the group as it knew it before dropping off. If it fails, if it can't, it can't. So it will eventually stop, and then the operator or DBA would have to come in and rejoin it. But in the meantime, if that doesn't happen and things are working just fine, A will rejoin normally and automatically. So monitoring, we also enhanced the performance schema tables with additional monitoring information, especially some work was done especially around keeping track of how far behind is a server with respect to its own master or its own primary. And this is because we've had, over the years, we've had a bunch of bugs associated with things like seconds behind master, which is really like not a reliable thing at all. So in 8.0, we did all this work to allow an easier calculation of lag when it comes, comparing how far behind this replica is or this server is with respect to its master. So now you can go into these performance schema tables and see, okay, how far behind am I with respect to the original master where this transaction was originally executed, right? In this case, you can go to D and say, okay, so how much far am I with respect to A in terms of time, commit times? And you can also say, how far am I with respect to my immediate master? In this case, between, if you go to C, how far am I with respect to B? So these are things that were introduced. This is metadata that was introduced into the bin log, and that is exposed. So it's a set of commit timestamps that we introduced into the bin log, and it is exposed on the replication performance schema tables. And they replace seconds behind master that way. Another thing that we did was actually, okay, so I know that I'm lagging. I know that this guy is not committing, immediately after my master. I know that there's network transmission time and so on and so forth, and then there's queuing time in the relay log and so on, and then there's apply time on the applier. So why or where am I spending the most time when I'm lagging, right? So through the performance schema tables, the new performance schema tables in MySQL 8 as well, you can inspect where transactions are actually spending more time in the replication pipeline. So you have timestamps for when a transaction was received, when it was read from the relay log, when it was applied, and so on and so forth. So you can kind of X-ray the execution on the applier this way. So more observability is always good, as long as it doesn't bring any severe performance issues. Also, more on the monitoring side, we extended this group replication performance schema tables to expose global data, as in you can go to any of these servers and say, okay, who's the primary in the group and what versions are these servers in the group on? So that you don't go to each and every server in the group and ask them this. Before MySQL 8 or in MySQL 7, I think this only added one row, the row for the local server. So if you would go to A, it will only say, okay, you know, this is me and these are my details. But now these tables show information about everybody, every server in the group. This, of course, comes at the cost of, there's some extra coordination when, servers join the group and whenever there's a failover, this coordination happens, but it's not in the critical execution path. It happens when the membership changes, basically. There's also ways to inspect somewhat very low-level things. I mentioned earlier, if A is away, is unreachable, but it's not kicked out of the group, there's a message cache that has to be kept at the group communication infrastructure. And just FYI, if you don't know, under the hood, our group communication engine is built on top of Paxos. So what happens here is that you can actually get a sense of how large this message cache is at this point in time. It's really a message pool, if you will. There's automatic garbage collection and all of these things that is handled without you having to do anything. But this gives you some way to inspect where memory is going into when at the group communication level. So performance, one thing we did was to make the applier faster by being able to parallelize more aggressively. And to do this, we relied on write sets. Write sets is basically a concept that we introduced with group replication, where a write set, the definition of a write set is basically very roughly, it's the set of primary keys of the rows that you changed during the execution of your transaction. So if you take this into account and you go to the slave and you are applying a bunch of transactions, you can try to intersect all these write sets, and if the intersection is empty, you can say, okay, these transactions are not conflicting, so I might just as well apply them in parallel. So that's basically it. We use this write set information to actually parallelize more aggressively on the slave, and this, of course, provided feedback into the group replication recovery phase, which is, when you add a server to the group, it has to catch up with the rest of the server, with the rest of the group, and it does so by using asynchronous replication. So the faster you can apply, the faster you can the faster you can synchronize with the rest of the group, and the faster you become online. So in addition to asynchronous replication becoming faster on the applier, it also means that the recovery time for a server that joins the cluster becomes smaller or shorter. This also means that it's, for some cases, for some workloads, like a single-threaded workload on the master, can actually be applied in parallel on the slave, as long as transactions that are executed on the master do not touch the same rows, right? So if you have transactions executing by a serial application in a sequential form, if each transaction changes different rows, these transactions can be applied in parallel on the slave. This is just a couple of figures to show you how how the time it takes to recovery has been, to recover when you add a server to the cluster to catch up. The time it takes to catch up for a new server in the cluster has been reduced when using right-side parallelization. So on the left-hand side, you see, the red bar is without right-side parallelization. The orange bar is with right-side parallelization. And the figures are when the system is running at 33% of its capacity, so you're running sysbench, but you're not overloading the system. And then on the right-hand side is when the system is running at 66% of the capacity. So more load, you're stressing more the system. So how much time does it take for a server that is joined or added to the group? How much time does it take, and how much time do we save before we catch up? We also fixed a few things on the applier in terms of contention and interoperability between receiver threads or IO threads and applier threads or SQL threads. There was some contention on some logs that protected the relay log. We fixed that, and because of that, we got some increased throughput on the applier. In the previous session, Sunny mentioned that we're doing this partial blob APIs and restructuring the blob infrastructure so that we can do things like partial blob updates. And that, of course, ripples all the way through replication as well, because for the JSON data type, we can actually do a logical delta of the changes. So if you have a document in MySQL, we can just replicate the field that you change instead of the full document. So it becomes much more efficient in terms of memory footprint, storage footprint, and network usage as well. This chart just shows that, of course, nothing is free. There's some cost to this because there's the additional calculation of the logical delta of the blob on the master. So there's some impact on the throughput on the master. But incidentally, there's some, the applier becomes faster because there's less for it to deal with. So there's less bytes to handle and process, to load, to store in the relay log, to load from the relay log, to move around in memory, and so on and so forth. So security, we added binary log encryption on disk in MySQL 8.0 So the overall design is more or less that of TDE. So you have one file encryption, one encryption key per file, and then you have a master key that protects this key for all the files. So this becomes easier to manage when it comes to rotating encryption keys and so on and so forth. But the main point is that each binlog file is encrypted on disk. It's not encrypted when you send it across the network, right? This is encryption on disk. As soon as it hits the disk, it's encrypted. When you load from the disk, we decrypt it. If we have to send it across, we send it across unencrypted. Of course, you should use SSL in that case if you're worried about protecting your data, on-transit data. And this is the main points here, really. You can actually turn it on and off dynamically, and you can have encrypted binlog files together with unencrypted binlog files or coexisting in the system, when you're turning on and off this feature. Relay logs are also encrypted, obviously. I mean, once the receiver thread or the IO thread receives the binlog from the master, it will write it to the relay log, and that's also encrypted if you have binlog encryption on the slave. Yes?
Are you compressing the binlogs before encrypting?
Are we?
Is there any thought to compressing the binlogs?
Compressing.
Because the binlogs can compress extremely well, and you've
Yeah, yeah. There's some work on compression that we are looking at. All right, good. And in addition to this, in 8.0.16, okay, so the story was not fully complete in 8.0.14 because, if you wanted to rotate the key, it required you to restart the server and set this option, and then this option, on recovery, if this option was set, it would rotate the key and only then bring the server up. In 8.0.16, we introduced this alter instance rotate bin lock key. So, if online, you can go in and force a key rotation without having to restart the server, basically. There's a bunch of other stuff. We changed a few defaults. The most interesting thing to highlight here is probably the binary log is on by default now. And that's basically it. That's the most clear change in the defaults, if you will. And a bunch of other stuff related to monitoring, operations, support for IPv6 and so on and so forth. That I'm not going to go into the details, but there's a bunch of blog posts for each and every thing that we've done, that we have written, which have a fair amount of details on the technical aspects of this. I'll give you the link at the end of the session, and just to conclude, it's been a hell of a ride. So it's really, this is a slide I like to bring up, mostly because I really like this slide because it shows up the roadmap or the road that we've been going through and progressing as we move forward. And there's a bunch of stuff that we've been delivering. But the interesting part is that all of this started, a few years ago when we took the time to say, okay, let's stop a little bit, let's think, let's take a step back, look at what we have today, look at what are the foundational changes that we need to do to be able to build this more advanced stuff on top, of technology that we have today, but also new technology that we really want to put out there. And this, 30th of September 2014 is a big mark in time, a big point in time, because it was the first time that some of that appeared out in the public, with the group replication preview on labs. A lot of the foundational work that we've done inside the server was then exposed through a new plugin that people could, try to use and break it and provide feedback. And that was really nice because over the years we also did a lot of feature previews with group replication. We got so much feedback that we have incorporated into the product as years went by. And we've reached this point, we're talking about 8.0.16 now with all these features and so on and so forth. So everything is converging. There's still a lot of work to do, but it's really nice seeing all of this coming together. And it also means that a lot of the work that we had been doing before, like GTIDs, like parallel slave, like all these things, they happened for a reason. Not just because of the reason that we all know, like GTIDs to facilitate failovers, okay, auto position and so on, great. But if you factor that into this roadmap of, for instance, group replication in DynamoDB cluster, it becomes much more clear of why these things were introduced and designed the way they were, actually. All right, so let's just finish this. We have a lot of this picture implemented already, but we want to do more. We want to do right scalability and so on and so forth, come up with solutions for sharding, automated sharding and so on. But this is we're executing, so things will come eventually, but that's where we are today. And just to conclude, this is not so relevant, but this is relevant. So if you want to try out MySQL 8, I think pretty much everybody knows where to find it. Documentation is in the reference manual, and as I mentioned earlier, there's a lot of technical blog posts on MySQLavailability.com. If you're into the gory details, that's where you can find a lot of interesting information. You can also grab me outside and talk a little bit more about the details. But a lot of the things I talked about here today, it's really like we will spend, I don't know, days and days talking about it. Anyway, so thanks for attending. Questions? No? All right. Oh, there's one here.
Is there any CPU load that the encryption puts on when there are not the binders on?
Yes, there's a CPU price to pay. We don't have benchmarks. We should have published that. To my knowledge, under Sysbench, it's not that big of a deal, but it obviously depends on the workload. So there's some penalty there. Depends on the use case. Yes?
In case of encrypted binary log, how master and slave should be configured to share the same encryption key?
To share the same encryption key.
Yeah, or how it's done?
You're not supposed to share the same encryption key between masters and slaves. That's the whole point. The keys should be local, basically. That's why you don't send anything encrypted across the network, basically.
So how the slave can decrypt data which was encrypted on the master?
The slave doesn't decrypt, that's what I'm saying. You write to the bin log, and that's encrypted when you write it. When you read from the bin log, it's decrypted. So when you send it across, it goes decrypted, right?
The consistent level is defined by yourself. Do you think that some other database will accept your defined the consistency level, such as read before and write after?
Can you rephrase? Sorry.
Yeah. I mean, the consistency level is defined by yourself, and it is new. Do you think some other database company may accept your consistency level, such as you have defined right after the read before?
Right. That's an interesting question. I don't know. So the question is, the consistency levels are defined by us in our designs, and that's how we designed it. Do you think if other databases will follow and do something similar? That's a hard question to answer. I think that other databases may come up with similar things if they haven't already, but it's hard for me to answer this in 20 seconds. Maybe we can talk outside. There was a question here?
It's okay, I will take it down.
Okay. Yes?
So in your consistency models with before and after, are you waiting for all transactions that are deployed?
Yes.
Okay, so you're not smart yet.
No. We don't build a dependency graph if that's what you're asking. We wait for we basically grab a slot in the total order of execution and say, when this slot is free to execute, I'll just execute it. Because then everything else before it was applied. So the history before it was applied.
I didn't know if you were taking into consideration flag sets.
No. That's an interesting optimization that we thought about, but it's a bit more complex than, easier said than done, basically. All right, so I guess we're done. Thank you very much.